Right now, something is wrong with the universe. Not somewhere far away. Not in a distant corner of space you'll never visit. Right now, above your head, in the sky you look up at every night. Something is wrong. And the most powerful telescope humanity has ever built looked up at that sky. And what it saw made scientists go completely silent. Not the silence of awe, the silence of confusion, the silence of not knowing what to say, the silence that falls over a room full of brilliant people when reality refuses to cooperate with everything they thought they knew. Because what James Webb found out there 13 billion light years away, in the earliest moments of the universe, should not exist. Not according to our models. Not according to our physics. Not according to anything we thought we knew. And yet, there it was, sitting in the data, unmistakable, undeniable, a problem too large to explain away. Galaxies, enormous, fully formed, mature galaxies, from a period when the universe was barely a few 100 million years old. A universe that should have been dark, raw, barely beginning, but instead filled with enormous, developed, ancient-looking galaxies. As the universe in those early years should look like the rough sketch of something, not the finished painting. Like a construction site, not a finished building. Like an infant, not a fully grown adult. Because making galaxies takes time, takes mergers. It takes matter slowly pulling together under gravity over vast timescales. It takes generation after generation of stars being born and dying and scattering their material into space. It takes the slow, patient accumulation of complexity. None of that can happen overnight. None of that can happen in a few 100 million years. At least that's what we thought. According to our model, large and mature galaxies should not exist in the first 1 to 2 billion years of the universe. It is physically impossible, because there isn't enough time. There isn't enough matter accumulated in any one place. There aren't enough merger events to build something that big. The first galaxies should be small, raw, irregular structures. Galaxy seeds still in the earliest stages of taking shape. Just like it's impossible for a newborn baby to run a marathon on its first day of life. The physics simply doesn't allow it. This is not a soft guideline or a rough estimate. This is one of the hardest, most well-tested predictions in modern cosmology. But James Webb saw the exact opposite. To truly understand what James Webb found, you first need to understand what James Webb actually is. Because this is not just another telescope. This is not simply a newer version of what came before. This is the most powerful space observatory humanity has ever built. The result of over 20 years of planning, engineering, testing, and redesign. The product of contributions from thousands of engineers and scientists across 17 countries. A machine so complex that its deployment was considered one of the most technically risky operations NASA had ever attempted. It was launched in December of 2021. It was positioned approximately 1.5 million kilometers from Earth, far beyond the Moon, far beyond any previous space telescope, at a gravitationally stable point in our solar system called the second Lagrange point. A place where the gravitational pulls of the Earth and Sun balance in a way that allows Webb to maintain a stable orbit with minimal fuel consumption. This primary mirror spans 6.5 meters in diameter, made of 18 individual hexagonal segments coated in gold. Yes, actual gold, because gold reflects infrared light better than almost anything else. And infrared light is exactly what Webb was designed to detect. Why infrared? Because the universe is expanding, and as it expands, light from distant galaxies gets stretched out. The wavelength grows longer. It shifts toward the red end of the spectrum, and for the most distant galaxies, the ones from the very earliest periods of the universe, that shift is so extreme that the light moves completely out of the visible range, into the infrared, beyond what human eyes can detect. Beyond what ordinary cameras can capture. beyond what Hubble could detect, but not beyond what Webb can detect. Webb was built specifically for this, built to see what nothing before it could see, built to reach back further in time than any instrument in human history. The previous generation Hubble Space Telescope was extraordinary in its own right. It changed how we see the universe. It gave us images of galaxies being born, galaxies colliding, stars exploding at the edges of the observable cosmos. It earned its place in history as one of the great scientific instruments of all time. But Webb's sensitivity is roughly 100 times greater than Hubble's. Think about what that means. If Hubble could see the light of a candle from a few hundred kilometers away, Webb could see that same candle from tens of thousands of kilometers away. It is not a marginal improvement. It is a leap of a different order entirely. With this sensitivity, Webb can look back further in time than any instrument before it. Back to the universe's very first chapters. Back to a period that has never been observed in detail before. And when it looked, it found something that should not be there. In the first James Webb data released publicly in 2022, astronomers began observing galaxies from the earliest periods of the universe, from just a few 100 million years after the Big Bang. Galaxies from an era that had previously been largely invisible to us. And these galaxies were not small and primitive. They were large, shockingly large, mature, fully developed, as if they had billions of years of history behind them. Their masses were comparable to the largest galaxies we see in the universe today. The number of stars inside them was in the hundreds of billions. When astronomers first looked at these galaxies, many of them thought something had gone wrong with the data. They checked the calibrations. They checked the pipeline. They checked the analysis code. Because what they were seeing was simply not possible. And yet, the data was clean. The instruments were working perfectly. The numbers were right. Scientists began methodically checking for errors. Maybe the redshift measurements were wrong. Redshift is the primary tool astronomers use to determine how far away a galaxy is, and therefore how old the light coming from it is. The more a galaxy's light has shifted toward red, the further away it is. And the further away it is, the further back in time we're looking. These measurements are extremely well understood. They have been used successfully for decades, tested against other methods, validated by independent teams using independent instruments. But maybe they were somehow off. Maybe there was a calculation error somewhere in the pipeline. Maybe there was a systematic bias in the telescope's calibration. Maybe something unusual about the light from these early galaxies was fooling the analysis software into placing them further away than they actually were. Every possibility was carefully and methodically investigated. Every number was checked again and again. Teams that had never worked together compared results. Competing groups tried to find each other's mistakes. But there was no error. The data was consistent. These galaxies were genuinely as far away as the measurements said, and therefore genuinely as old as they appeared, and therefore genuinely should not be that large. But they were. This discovery did not just surprise the cosmology world. It shook it deeply, fundamentally, because we're not talking about one or two unusual galaxies. We're talking about dozens, then hundreds, across different parts of the sky, confirmed by multiple telescopes and multiple teams independently, all of them showing the same thing. Enormous, mature galaxies in a period when enormous, mature galaxies should not exist. Astronomers began calling these structures cosmic titans, enormous, mysterious, inexplicable entities that seem to defy the rules the universe is supposed to follow. Structures that sit in the data like a challenge, like a question written in light, like the universe saying, "Try to explain this." But here is where the story becomes truly disturbing, because it's not just their size that's wrong. These galaxies are not only too large for their age, they are also too old for their age. The stars inside them are not young. They are mature. Red and yellow stars dominate, the same kinds of stars that take billions of years to develop. Stars that speak of a long history, a history the universe hadn't had time to write. This points to a period of intense star formation that apparently happened, reached its peak, and then slowed down, all within a time frame where it should never have started at all. Where did that time come from? How did billions of years' worth of stellar evolution happen in a fraction of that time? How did these galaxies grow old before the universe was old enough to age them? The more you think about this question, the deeper the problem gets. It's not just that these galaxies exist when they shouldn't. It's that their entire history is impossible, as if time itself has been fast-forwarded inside these structures, as if the universe gave them a head start that no model can account for. The universe was still an infant, but these galaxies already looked old. How is that possible? And this is where the greatest crisis in modern cosmology begins. To truly grasp the depth of this crisis, we need to look more carefully at how galaxy formation is actually supposed to work. How does a galaxy form? The question sounds simple. The answer is not. And understanding the answer, truly understanding it, is the only way to appreciate how deeply impossible these early galaxies are. It begins with dark matter. In the moments after the Big Bang, the universe was nearly, but not perfectly, uniform. Tiny variations in density existed everywhere. Some regions were very slightly denser than others. The difference was almost nothing, a fraction of a percent at most. But those tiny variations were enough. These tiny differences, driven by quantum fluctuations in the earliest moments of the universe, set the stage for everything that came after. Dark matter, the invisible substance that makes up roughly 27% of the universe's total mass, began to drift toward these denser regions. As it accumulated, its gravitational pull grew stronger, and it began pulling in normal matter, primarily hydrogen and helium gas, along with it. This process was slow, enormously slow, but it was steady. And over hundreds of millions of years, it built the scaffolding for everything that would follow. Slowly, these gas clouds collapsed under their own gravity. They compressed, they heated up, and at a certain critical threshold, the temperature and pressure at the center became high enough to trigger nuclear fusion. The first star ignited, a moment of extraordinary significance, the first light in the cosmic dark ages. As more gas flowed in, more stars formed around it. A small galaxy was born. Over hundreds of millions of years, this small galaxy encountered other small galaxies and merged with them. The merged galaxy grew larger, emerged again, and billions of years after the process began, galaxies the size of the Milky Way emerged. Patient, gradual, built from the bottom up over cosmic timescales. This process, called hierarchical galaxy formation, is one of the most well-tested ideas in modern cosmology. Simulations of this process match observations across billions of years of cosmic history with extraordinary accuracy. It is not a guess or a speculation. It is not a rough approximation. It is supported by mountains of evidence gathered over decades by thousands of researchers using dozens of different observational techniques. We know how galaxies form, or we thought we did. And according to this process, the galaxies James Webb observed cannot exist. Not at that age, not at that size, not with that level of stellar maturity. The merger events needed to build them hadn't happened yet. The time needed for stellar generations to come and go hadn't passed. The raw material hadn't gathered into place. Nothing about these galaxies should be possible. It's as impossible as a child winning an Olympic marathon before learning to walk. The development simply cannot have happened in the time available. But those galaxies are there, confirmed, real, undeniable, and that means one of two things. Either our model of galaxy formation is fundamentally wrong, or there are mechanisms operating in the early universe that we have never encountered and do not currently understand. Either way, something we believed about the universe is not correct. And figuring out what that something is may be the most important challenge in all of modern cosmology. To answer this, scientists have proposed several hypotheses, each one more striking than the last. Each one trying to save the standard model while acknowledging that something unusual must have happened. The first hypothesis is that the early universe was simply far more efficient than we thought. That star formation happened at rates hundreds or thousands of times higher than anything we see in the modern universe. That matter pulled together not over billions of years, but over tens or hundreds of millions. That the early universe was running at a pace our models never anticipated. That somehow, in those first few 100 million years, the universe compressed billions of years of evolutionary work into a tiny fraction of that time. This is possible, but it creates serious problems of its own. Star formation at those rates requires enormous amounts of raw material delivered at an extraordinary pace. It also produces enormous numbers of supernova explosions as those stars die. And those explosions release so much energy that they should blow the surrounding gas away, stopping the very star formation they came from. In our models, this feedback mechanism limits how fast galaxies can grow, a kind of natural speed governor, a thermostat built into the physics of star-forming regions. But these early galaxies appear to have grown right through it, as if that feedback mechanism simply didn't apply, as if the governor was disabled, as if something overrode the natural limits and allowed the growth to continue unchecked. The second hypothesis is that dark matter in the early universe behaved differently than it does today, that it clumped together faster, that it created denser gravitational wells earlier, and that normal matter fell into those wells more rapidly as a result. Dark matter pulling everything together faster than we thought possible, creating the conditions for galaxy formation on a dramatically accelerated timeline. This too is possible, but it requires changing our models of dark matter in ways that conflict with other well-established observations. In particular, the cosmic microwave background radiation, the afterglow of the Big Bang, provides extremely precise measurements of how matter was distributed in the early universe. And those measurements strongly support the standard dark matter model. Changing dark matter's behavior to explain these galaxies would break our ability to explain other things we observe. You cannot fix one problem without creating several new ones. The universe doesn't allow that kind of easy solution. The third hypothesis involves black holes. Specifically, enormous black holes forming in the very early universe and acting as engines for rapid galaxy growth. By consuming surrounding gas at extraordinary rates and releasing huge amounts of energy, these black holes could potentially create conditions that accelerate galaxy formation dramatically, like a catalyst in a chemical reaction, speeding up something that would otherwise take far longer. And James Webb has indeed detected unexpectedly large, unexpectedly active black holes at the centers of some of these early galaxies. Their masses are in the billions of solar masses, active and radiating at extraordinary intensities, blazing with the light of matter falling into them. Quasars, the brightest individual objects in the known universe, appearing in numbers and at times when they should not yet exist. This hypothesis has some observational support, but it doesn't explain everything, because not every unusually large early galaxy has an extraordinarily active black hole at its center. Some are growing rapidly even without that apparent engine. And even for the ones that do have massive active black holes, those black holes themselves are too massive, too early, and present their own version of the same problem. The explanation reaches for something it cannot fully grasp. The fourth hypothesis is the most radical. Maybe our standard cosmological model, the entire framework we use to describe the history of the universe, is fundamentally incomplete in ways we haven't yet recognized. Maybe cosmic inflation, the period of explosive expansion in the universe's very first fraction of a second, didn't unfold exactly as we modeled it. Maybe some regions of the universe were seeded with conditions that allowed structures to form far faster than our standard models predict. Maybe there are aspects of the earliest moments of the universe that we simply don't understand yet. Aspects that we have been assuming away, filling in with guesses that seemed reasonable, but that turn out to be wrong when James Webb's data forces us to check. This is the hypothesis scientists are most reluctant to accept, because the standard cosmological model has been confirmed so thoroughly. Cosmic microwave background radiation data, baryon acoustic oscillations, large-scale structure surveys, all of it points to the same underlying framework. Discarding it, or even significantly revising it, means overturning decades of work by thousands of researchers. It means questioning things that generations of scientists have built their careers on. It means admitting that the map we've been using to navigate the universe is missing something important. Something we didn't know was missing, until now. But James Webb's data keeps arriving, month after month. And every new observation confirms that these unusual early galaxies are not a fluke. They are not the result of a single bad measurement. They are not a statistical quirk. They are a real feature of the early universe. Widespread, consistent, confirmed by independent teams using independent methods, and currently without a fully satisfying explanation. A study published in 2023 put the problem into stark relief. Researchers found that some of these early galaxies appeared to have converted nearly all of the available matter in their region of the universe into stars. Not most of it, almost all of it. Zero waste, zero leftovers, an efficiency of star formation that no current model can reproduce. Not even close. And the fact that this happened as early as it did makes the problem even more severe. As if the universe somehow knew exactly what to do with every atom of available gas. As if there was no trial and error, no inefficiency, no material left unconverted. Just a perfect, relentless transformation of raw gas into stars. At an age when raw gas shouldn't even have gathered into structures yet. Think about what that means. In one region of space, virtually all available raw material was converted into stars and galaxies in a tiny fraction of the universe's total age. Nature almost never works that efficiently, in any domain, at any scale, and yet here it is, written in light that has been traveling toward us for 13 billion years, waiting in the data for a telescope powerful enough to read it. But the most disturbing part of the story hasn't arrived yet. Because in some of these early galaxies, scientists noticed something even stranger. Something that goes beyond the simple question of size. The stars inside these galaxies are not just old. They belong to ancient stellar generations. They are not the first generation of stars. They were born from the remnants of stars that already lived and died before them. Those earlier stars formed in the very first moments after the Big Bang. They burned bright and fast, enormous, hydrogen-rich, blazing with a ferocity that no star in today's universe can match. And they exploded as supernovae. Their explosions scattered heavy elements, carbon, oxygen, iron, nitrogen, into the surrounding gas. And the next generation of stars formed from that enriched material. This is supposed to take many millions of years per generation. Multiple generations, building up slowly cycle by cycle. Each generation standing on the ashes of the one before. But the heavy element content of some of these early galaxies implies that multiple stellar generations had already come and gone by the time these galaxies were observed. In a universe that was only a few 100 million years old. Not one generation, multiple generations, cycle after cycle of stellar birth and death, all happening in a time frame where the standard model says even the first generation was barely getting started. The math does not work. The timeline does not fit. And yet the evidence is there, written in the spectrum of light, in the chemical fingerprints of elements that should not yet exist in those quantities, in the spectral lines that don't lie. We keep arriving at the same question. Where did the time come from? There is no satisfying answer. Not yet. And scientists openly admit this. Not quietly in private, but publicly, in the journals, in the conferences. A paper published in Nature stated it clearly. James Webb's observations are incompatible with our current understanding of galaxy formation. Either there is a systematic error in our observations, or there is a fundamental gap in our knowledge of physics. The second possibility is far more unsettling, because it means the universe has been keeping a secret hidden in the light of those earliest galaxies, a secret that waited 13 billion years for a telescope powerful enough to read it. And now we've read it. We just don't understand what it says. Step back and take in the full picture. You have the most powerful telescope humanity has ever built. It is showing you the earliest chapters of the universe's history. And what it shows you is this: large galaxies where there should be small ones, mature galaxies where there should be primitive ones, heavy elements where there should be almost none, massive black holes where there should be tiny ones, everything in the wrong place, everything at the wrong time, a universe that looks older than it should, a universe that built itself faster than physics allows, a universe that ignored our best predictions and did something else entirely. This is not a small anomaly. This is not a rounding error. This is a crisis, a genuine, deep, unresolved crisis in our understanding of how the universe works. And it doesn't just affect our understanding of galaxy formation. It affects our understanding of the entire history of the universe, from its very first moments to the conditions that allowed us to exist. But for now, know this: these galaxies are real. This data is real. And the implications are real enough that some of the most respected cosmologists in the world are now saying openly, maybe we don't know as much as we thought. Maybe the universe is far more complex than our best models suggest. Maybe James Webb has only just opened the door. And what lies behind that door, we are only beginning to glimpse. What is inside these impossible galaxies? What mechanism could have made them so large, so fast? And how do the enormous black holes lurking at their centers fit into this picture? In the next section, we're going to look closer, much closer. We're going to step inside these galaxies and examine what they contain. And every answer we find will raise a deeper question, because this story is not about a few unusual galaxies. This story is about the universe itself, and what we might have gotten wrong about it. Close your eyes for a moment and think about this. Right now, more than 13 billion light years away, there are galaxies that should not exist. They are still there, still shining, still burning with the light of hundreds of billions of stars. And that ancient light, that 13-billion-year-old message from the edge of time, is traveling toward you right now, crossing distances that dwarf any scale the human mind was built to comprehend. And when it reaches you, it carries one simple, impossible truth. The universe is far stranger than we ever imagined. Stepping inside a galaxy. Think about that for a moment. Really think about it. We are already inside a galaxy. The Milky Way surrounds us in every direction. 200 billion stars at minimum. A disk of gas and dust and dark matter 100,000 light-years across. We are embedded in the middle of it, roughly 2/3 of the way out from the center. But we can't see it from the outside. We are like a single cell inside a vast organism, unable to perceive the shape of the whole. unable to step back and see the structure we inhabit. But James Webb, peering across billions of light-years of space, can look at other galaxies from the outside. It can examine their structures, their compositions, their internal dynamics. It can study them with a clarity and precision that was unimaginable just a few years ago. And when it turned that extraordinary gaze on the impossible early galaxies, what it found inside them was as strange as the galaxies themselves. Strange enough to deepen the mystery rather than resolve it. Strange enough to suggest that whatever is happening in the early universe, it is not simply a matter of galaxies forming faster than expected. Something more fundamental is at work. To understand what makes the inside of these galaxies so unusual, we first need a baseline. We need to understand what the inside of a normal galaxy looks like. Something to compare against. Because without a comparison, the strangeness is hard to measure. Without knowing what ordinary looks like, we can't recognize the extraordinary. Think about the Milky Way, a mature, middle-aged galaxy in the present-day universe. About 13.5 billion years old. A galaxy that has had time to go through many phases. Turbulent youth, settling middle age, and now a kind of steady, self-sustaining maturity. Inside it, roughly 200 to 400 billion stars. Most of them middle-aged or old. Yellow dwarfs like our own sun. Orange giants approaching the end of their lives. Red giants, white dwarfs, neutron stars. The full spectrum of stellar evolution, represented across a galaxy that has had billions of years to accumulate its complexity. New star formation is happening, but slowly. Just a few solar masses of new stars per year. Not a frantic burst of creation. A steady, gentle pace. A galaxy in maintenance mode, not construction mode. At its center, a supermassive black hole called Sagittarius A*, with a mass of about 4 million suns. Currently quiet. Currently just sitting there, not consuming much, not radiating intensely. A sleeping giant at the heart of a calm, orderly system. Calm, predictable, well-behaved galaxy. The kind of galaxy our models expect to see in a 13.8 billion-year-old universe. The kind of galaxy that took billions of years to become what it is. Now look at one of James Webb's impossible early galaxies. From just 500 to 700 million years after the Big Bang. When the universe was barely 5% of its current age. 5%. When barely anything should have had time to develop. When the universe should still have been a relatively simple, relatively undeveloped place. What's inside it? The first thing that strikes you is the star formation rate. These galaxies are producing new stars at rates that are hundreds, in some cases thousands, of times higher than what we see in a galaxy like the Milky Way today. Not a few solar masses of stars per year. Hundreds of solar masses, sometimes thousands, every single year, year after year, without pause, without apparent limit. The galaxy is essentially consuming its own gas supply at a furious pace. Stars being born and burning their fuel so rapidly that the entire galactic environment is lit up from within. As if every cubic light year of space inside the galaxy is on fire. As if the galaxy has been given no choice but to burn everything it has as fast as it possibly can. Racing toward some unknown threshold at a speed that nothing in our current understanding can explain. But this frantic star formation creates a puzzle all by itself. Because star formation at those rates requires enormous amounts of cold gas being continuously delivered to the galaxy. A constant supply of raw material. A pipeline of gas flowing in from somewhere. And in the standard model, that supply comes from cosmic filaments, the thin threads of the cosmic web that connect galaxy clusters to each other and feed cold gas streams into growing galaxies. But in the early universe, those filaments were still in their infancy. They hadn't fully developed yet. The supply network wasn't in place. The infrastructure wasn't built. And yet these galaxies somehow have the raw material they need. Somehow the gas is arriving. Somehow the star factories are running at full capacity, despite the fact that the infrastructure to support them shouldn't exist yet. Despite the fact that the pipelines that feed them shouldn't be open. Something is delivering the fuel, and we don't know what. The second thing that strikes you is the contradiction between the star formation rate and the apparent age of the stellar population. If star formation is running at this frantic pace, if the galaxy is essentially brand new and burning through its first supply of gas, then you would expect to see mostly young stars. Hot, blue, bright, newly born. The kinds of stars you find in a galaxy that's just getting started. Fresh, energetic, burning with the intensity of youth. But that's not what James Webb sees. Alongside the young stars, there are old stars, red and yellow stars, stars that take billions of years to develop, stars that indicate an already long history of star formation, a period of intense activity that has already slowed down, as if the galaxy has lived through its turbulent youth and already begun to settle into middle age. All while the universe itself is still a teenager. The galaxy is simultaneously brand new and ancient, both things, at the same time, in the same structure, burning with new star formation on one hand, carrying the quiet evidence of an ancient stellar population on the other. These two facts should be mutually exclusive, and yet both are written in the data. To illustrate how strange this is, consider an analogy. You're examining a person. By all physical markers, they appear to be about 5 years old. Small, growing, developing. But when you look at their bones, their internal organs, their cellular biology, you find the body of a 50-year-old. Decades of wear and aging packed into a body that should only be 5 years old. That would be medically impossible. It would stop doctors in their tracks. It would demand an explanation that standard medical science simply could not provide. It would indicate something deeply wrong with our understanding of human biology. And yet that is essentially what James Webb is finding inside these early galaxies. Both young and old. Both just beginning and already ancient. A contradiction written in stars. A biological impossibility scaled to cosmological proportions. The third striking thing is the abundance of heavy elements. The Big Bang produced only 3 elements in any significant quantity: hydrogen, helium, and trace amounts of lithium. Everything heavier than that, every carbon atom, every oxygen molecule, every iron nucleus, had to be forged inside stars, built through nuclear fusion in stellar cores, and then scattered into space when those stars died. This process is called stellar nucleosynthesis. It is one of the most beautiful and important processes in all of physics. The stars are not just burning gas. They are factories, manufacturing the raw materials of chemistry, of geology, of biology, building the atoms that eventually make up planets and people and everything else. And this process is generational. It requires multiple cycles of star birth and death to build up a meaningful abundance of heavy elements. Each generation leaves behind a richer legacy than the one before. Each supernova scatters more heavy material into the surrounding gas. And each new generation of stars forms from a slightly richer mixture. In the early universe, this process should barely have begun. A few 100 million years is not enough time for multiple generations of stars to complete their cycles. The chemistry should still be simple. The gas should still be mostly hydrogen and helium. The heavy elements should be present only in the most trace quantities. And yet James Webb detects significant amounts of carbon and oxygen in some of these early galaxies. Elements that should barely be present. Elements whose existence in these quantities requires far more stellar generations than the timeline allows. The numbers don't work. The ages don't match. The chemistry tells a story of a long and complex history that the universe simply hadn't had time to write yet. Scientists tried to calculate exactly how many stellar generations would be needed to produce the heavy element abundances observed. The answer was 3 to 5 generations at minimum, each generation taking millions of years. So at least 10 to 15 million years just for the heavy element enrichment, on top of everything else that supposedly happened to build these enormous mature galaxies. In a universe that was only a few 100 million years old. The timeline is impossible, and yet the evidence is there, written in the spectrum of light coming from galaxies at the edge of the observable universe. Patient, precise, undeniable. The fourth and perhaps most staggering thing James Webb found inside these early galaxies is what's sitting at their centers. Black holes. Massive black holes. Not just massive for the early universe, massive by any standard. Some of them equivalent to hundreds of millions or even billions of solar masses. Fully formed supermassive black holes, sitting at the hearts of these impossible galaxies, exactly where you would find them in a modern, mature, well-evolved galaxy. As if someone had simply transplanted the core of a modern galaxy into a universe that was barely old enough to have formed its first stars. And the problem is the same problem we keep running into. How did they get so big so fast? What process could have produced objects of this mass in a universe this young? Black holes grow by consuming matter. Material spirals inward, forms a swirling disk around the black hole, heats up, and gradually falls in. This process is real. It is observed. It is well understood. We can watch it happening in active galaxies right now. But it is not fast. There is a fundamental speed limit on how quickly a black hole can grow. This limit is called the Eddington limit. It arises because as a black hole consumes matter, the infalling material releases radiation, intense radiation, and at a certain consumption rate, that radiation pressure becomes strong enough to push new matter away, literally blowing away the food supply. The black hole effectively limits its own growth rate, a built-in speed governor, a natural constraint on how quickly these objects can accumulate mass. For a black hole to grow from a stellar mass object, a few tens of solar masses to a billion solar masses, our models say it takes billions of years, even under optimal conditions, even with the Eddington limit constantly being approached but not exceeded. Billions of years. Patient, continuous accretion over vast cosmic timescales. Not hundreds of millions. Not in the blink of cosmic time that the universe had available in those early chapters. And yet here are these billion solar mass black holes, sitting at the centers of galaxies in a universe that is only a few 100 million years old. Impossible by the physics we know, but undeniably present. Some scientists have proposed a mechanism called super Eddington growth, a way for black holes to consume matter faster than the standard limit suggests. This is theoretically possible under very specific conditions. Conditions involving unusual configurations of the infalling gas, unusual magnetic field geometries, unusual radiation environments. But those conditions are extreme. And for super Eddington growth to explain all of these early massive black holes, those extreme conditions would have had to be widespread throughout the early universe. Far more widespread than our models predict. So common as to not be exceptional at all, which would require explaining why they were so common, which brings us back to the same unsolved problem. Another proposal is called direct collapse. Instead of starting as a small stellar remnant and slowly growing, maybe some of these early black holes formed directly from the collapse of enormous primordial gas clouds. No star phase, no slow accumulation, just a vast cloud of gas, perhaps millions of times the mass of the Sun, collapsing directly into a black hole in a single catastrophic event. Starting enormous from day one, already a supermassive object before a single generation of stars had time to die. This is a compelling idea. It would immediately solve the problem of how black holes became so massive so quickly. It would sidestep the Eddington limit by simply starting from a much higher initial mass. But the conditions required for direct collapse are very specific and very delicate. The gas cloud needs to be large enough, dense enough, and critically, the environment needs to be relatively free of certain types of radiation that would otherwise trigger star formation inside the cloud, preventing the direct collapse from happening. Maybe in the early universe, these conditions were more common. But were they common enough to explain all the enormous black holes James Webb is finding? We don't know. And not knowing is beginning to feel uncomfortable in a way it didn't before James Webb launched. The relationship between these black holes and the galaxies around them is one of the most fascinating parts of this mystery. Because black holes are not just passive passengers inside galaxies. They actively shape their hosts. They are not just objects. They are forces. They are participants in the evolution of the galaxies they inhabit. When a black hole is consuming matter at a high rate, it produces jets and winds of unimaginable power. Energy blasting outward at nearly the speed of light, reaching across tens of thousands of light years, heating the gas, pushing it away. This energy heats the surrounding gas, and heated gas doesn't form stars. So paradoxically, an actively feeding black hole can suppress star formation in its own galaxy, acting as a kind of cosmic thermostat, limiting how fast the galaxy grows, simultaneously feeding from the galaxy and constraining its growth. A relationship of extraordinary complexity. But in the early universe, something seems to have broken this regulation. Or perhaps it worked differently. Or perhaps the regulation mechanism itself was part of what drove these galaxies to grow so rapidly in the first place. A violent feedback cycle that simultaneously powered and constrained the furious activity inside these structures, driving both the growth and the limit on growth, creating conditions unlike anything we observe in the modern universe. James Webb has detected some extraordinary quasars, ultra-bright active galactic nuclei, in the early universe, blazing at intensities that outshine entire galaxies. Far more of them than expected, shining at distances that should have been too early, all of them in periods when they shouldn't yet exist, all of them surrounded by galaxies that shouldn't yet be so large. The pattern is unmistakable. The black holes and the galaxies grew together, rapidly, in concert, in ways we don't fully understand, in a universe that was supposed to be too young for any of it. A coevolution at the edge of the possible, or perhaps beyond the possible, depending on which physics you choose to trust. On one side, we have the standard model, decades of research, thousands of scientists, confirmed by observation after observation, a framework that has successfully predicted and explained so much of what we see in the universe. A framework that deserves enormous respect and has earned enormous confidence. On the other side, we have these data points from James Webb, impossible galaxies, ancient stars where there should be young ones, heavy elements where there should be almost none, massive black holes where there should be tiny seeds, a universe that looks decades older than it should. Something has to give. Either the standard model is missing something fundamental, something it has been missing all along, hidden behind the observational limits of previous telescopes, or the universe in its earliest chapters was operating by rules we haven't yet discovered. Either way, the story is the same. We are standing at the edge of the known, and James Webb is showing us how much lies beyond it. More than we expected. More than we prepared for, more than our best theories predicted. When you look up at the night sky tonight, know this. Out there, invisible to your eyes but real beyond any doubt, there are galaxies that lived impossible lives. Galaxies that formed in defiance of the physics we thought we understood. Galaxies whose very existence is a message to us. A message that says, you do not know as much as you think. The universe has more to say, and James Webb is only beginning to help us listen. In the next section, we're going to go deeper, past the star formation rates, past the black holes, into the structure of these galaxies themselves, their shapes, their chemistry, the very way they are put together, because that is where some of James Webb's most disturbing discoveries are waiting. Discoveries that challenge not just our models of galaxy formation, but the laws of physics themselves. Discoveries that suggest the wrongness of these early galaxies is not just about how they grew. It is about what they fundamentally are. Galaxy size, black hole mass, star formation rate. These are the anomalies we've been discussing. And by themselves, they constitute the greatest crisis in modern cosmology. A crisis that has been growing since the first James Webb data was released. A crisis that deepens with every new observation. But the story doesn't end there. Not even close. Because James Webb has found something even deeper. Something that goes beyond the question of how these galaxies grew so fast. Something that challenges the very way we think about the structure of the universe. Something that suggests the problem is not just with our timeline, but with our understanding of what a galaxy is and how one is built. In this section, I want to tell you something that may be the most unsettling thing James Webb has revealed. These unusual early galaxies are not just too big for their age. They are structurally wrong. Their shapes don't match what they should be. Their internal chemistry defies what we expect. Their very architecture contradicts everything our models predict about how galaxies should look at this stage of the universe. Wrong in ways that go beyond mere size. Wrong in ways that reach into the fundamental physics of how matter organizes itself. And this wrongness, this deep, pervasive structural wrongness, points to something much larger than a problem with galaxy formation. It points to a problem with our understanding of physics itself. Let's begin with shape. In the modern universe, galaxies come in a small number of recognizable forms. Spiral galaxies, flat, rotating disks with winding arms of stars and gas, like the Milky Way. Elliptical galaxies, smooth, rounded, featureless structures made mostly of old stars. And irregular galaxies, chaotic, asymmetric structures usually the result of a collision or merger. This classification system, developed over decades of observation, is not arbitrary. Each galaxy type represents a different stage or pathway in galactic evolution. The shapes of galaxies carry information about their histories, about what they've been through, about how old they are and how they got that way. Young, actively star-forming galaxies tend to be irregular or spiral. Old, passive galaxies, the ones that have burned through their gas and quieted down, tend to be elliptical. This pattern holds across billions of years of cosmic history, in every corner of the observable universe, tested and confirmed across thousands of galaxies, until you reach the galaxies James Webb is looking at. Some of these early galaxies are extraordinarily compact. Not just small, but small in a very specific and bizarre way. Their physical diameter is surprisingly limited, but the number of stars packed inside them is enormous. The stellar density, the number of stars per unit volume, is hundreds to thousands of times higher than in a typical galaxy today. Imagine taking all the stars in the Milky Way and compressing them into a space 10 or 20 times smaller. The distance between neighboring stars would shrink from light years to fractions of light years. The sky as seen from any planet in such a galaxy would be ablaze with nearby stars. Multiple bright suns visible at once. The night sky barely dark. The gravitational interactions between neighboring stellar systems constant and violent. The environment would be nothing like anything we experience here in our quiet corner of the Milky Way. And it would be nothing like anything our models predict for galaxies this young. This extreme compactness is itself a mystery. Our models of galaxy formation don't produce galaxies this dense. Not even close. When cosmological simulations try to create galaxies with these densities, something always goes wrong. Either the galaxy becomes unstable and tears itself apart, or the density drives such extreme star formation that the resulting feedback, the radiation and winds from the massive stars being born, blows the structure apart before it can consolidate. Or the simulation just fails to converge on anything resembling what James Webb is seeing. The parameters fight back. The physics pushes the simulation away from these configurations. And yet these galaxies exist, stable, intact, apparently having formed and survived despite all the reasons they shouldn't be able to, sitting calmly in the data, defying the simulations, waiting for an explanation. But the compact galaxies, as strange as they are not the most disturbing anomaly James Webb has found in terms of galaxy structure. That title belongs to something else entirely. Disk galaxies. A disk galaxy, the flat, rotating, spiral arm structure like our own Milky Way, is not supposed to form quickly. Not quickly at all. The disk structure emerges gradually through a process that takes billions of years to complete. A gas cloud collapses under its own gravity. As it collapses, conservation of angular momentum causes it to spin faster. Material in the plane of rotation is supported against further collapse by this spin. But material falling in from above and below the plane is not supported. It falls inward. The cloud flattens. Stars that form within the rotating disk inherit its orderly, organized motion. Over billions of years, spiral arms emerge from gravitational instabilities in the rotating disk. Intricate, beautiful, mathematically precise patterns. The signature of matter organized by rotation and gravity over cosmic timescales. This entire process is slow, gradual, patient, and it takes multiple billions of years to produce a well-ordered disk. James Webb found perfect disk galaxies from a period when the universe was only 600 million years old. 600 million years, out of nearly 14 billion, when the universe was barely 4% of its current age. One of them, designated Source 2112, became famous in the scientific community when it was described in a 2023 paper in Nature Astronomy. This galaxy has a clear, organized, disk structure, with what appear to be spiral features, orderly rotation, a settled, mature morphology, in a universe that is less than 5% of its current age. Researchers who described this galaxy acknowledged openly that it should not exist. The time needed to form a disk this ordered simply was not available, not even remotely, and yet, there it is, photographed, spectroscopically analyzed, confirmed by multiple independent teams. A disk galaxy where no disk galaxy should be. A contradiction in images. Puzzle made of light. The researchers who discovered Source 2112 suggested it might indicate that the early universe was more ordered than we thought. More structured. More organized from the very beginning. As if the initial conditions of the universe somehow set things up to develop rapidly in ways our models don't capture. But this only deepens the mystery rather than resolving it. Because if the early universe was already more ordered, more structured, then what made it that way? Where did that order come from? How do you get cosmic order before you've had time to build it? What sets things up so precisely that a fully organized disk galaxy can exist less than 1 billion years after the universe began? These questions have no answers yet. Only the uncomfortable awareness that the data is telling us something our theories are not equipped to receive. Now let's go to the chemical evidence, because this is perhaps the most technically damning of all the anomalies. And understanding it requires understanding how the universe's chemical complexity was supposed to develop. The story of how the elements were made. One of the great discoveries of 20th century astrophysics. The Big Bang produced three elements in any significant quantity: hydrogen, helium, and trace lithium. That's it. The entire periodic table, every element from carbon to uranium, had to be built later, inside stars, through nuclear fusion. This is the origin of the famous saying, "We are made of star stuff." The atoms in your body, the molecules in your DNA, the iron in your blood, all of it was forged in stellar interiors, scattered by stellar explosions, and eventually incorporated into the cloud of gas that became our solar system. The stars are the universe's element factories, and stellar nucleosynthesis, the process by which stars build heavy elements, is one of the most well-established ideas in all of astrophysics. We understand it in extraordinary detail. We can predict with great precision what mix of elements each generation of stars will produce and scatter. The theory is beautiful. The observations confirm it. Everything fits in the modern universe. The story is supposed to go like this. The first generation of stars, called population 3 stars, formed from almost pure hydrogen and helium. They were enormous, far more massive than most stars today. Hundreds of times the mass of our sun in some cases. They burned furiously and briefly, a few million years of existence, a cosmological eye blink. Then they exploded as supernovae, enriching the surrounding gas with the first heavy elements. The next generation of stars formed from this slightly enriched mixture. They too burned, died, and enriched the gas further. Each cycle built on the last. Slowly, generation by generation, the universe's chemical complexity grew. And this process takes time. Millions of years per stellar generation. Many generations to build up any significant heavy element abundance. The universe is supposed to be chemically primitive in its early chapters. Simple, dominated by hydrogen and helium, with only the faintest traces of anything heavier. The chemistry of the universe is supposed to grow richer slowly. Not all at once. Not early. Slowly, patiently, over billions of years. But James Webb is finding significant carbon and oxygen in galaxies from the universe's first few 100 million years. Abundances that imply 3, 4, 5 generations of stars have already come and gone. Abundances that by the math simply should not be there yet. The elements are present when they have no right to be present. And the problem isn't just the quantity, it's the ratios. The ratio of oxygen to hydrogen is wrong. The ratio of carbon to nitrogen is wrong. Not slightly off. Significantly different from what our models of stellar nucleosynthesis predict for this early stage of the universe. These ratios suggest that either the first generation of stars was fundamentally different from what we've modeled, producing unusual abundances through unusual nuclear processes, or that nuclear fusion itself was somehow different in the early universe, operating under different rules, producing different outputs, following different equations. Each of these possibilities is deeply troubling. If nuclear fusion worked differently in the early universe, that implies the physical constants that govern it, the strength of the nuclear force, the masses of fundamental particles were different then than they are now. And physical constants, by definition, should not change. The entire framework of modern physics depends on them being constant. Everywhere, at all times, in every corner of the universe. If they were different in the early universe, then the foundations of physics are shakier than we thought. The ground beneath our equations is not as solid as we assumed. Some observations do hint, very tentatively, that certain constants may have been slightly different in the distant past. Analysis of light from ancient quasars has suggested that the fine structure constant, a number that governs how matter and light interact, may have been subtly different billions of years ago. The evidence is not conclusive. It is hotly debated. Many researchers dispute both the data and the interpretation. But it exists. The hint is there. And James Webb is adding new data points to that debate with every observation, slowly building a picture that may eventually be impossible to dismiss. Now step back and look at all of these anomalies together. Not just the size of these galaxies, not just the black holes, not just the star formation rates, but all of them at once. The compactness, the disk structures, the heavy element abundances, the anomalous chemical ratios, all of it, together. When you look at them all together, a pattern emerges. These anomalies are not independent of each other. They are not a random collection of unrelated puzzles. They are all pointing in the same direction. They are all suggesting that the early universe was operating with a speed, an efficiency, and an organization that our current models cannot reproduce. Something was happening in the early universe, some mechanism, some process, some set of conditions that allowed structure to form faster, chemistry to develop faster, and complexity to emerge faster than our standard model says is possible. This is not a handful of isolated errors. This is a systematic difference between what we predicted and what we find. A consistent departure from our expectations, showing up in galaxy after galaxy, in observation after observation, in dataset after dataset, and systematic differences are never just rounding errors. They are signals. They are the universe trying to tell us something. What is it trying to say? Some scientists have proposed ideas at the outer edges of what is currently considered serious science. Ideas that a few years ago would have been dismissed without a second glance, but that James Webb's data has made impossible to simply wave away. Maybe the early universe was governed by slightly different physical laws. A universe where gravity was stronger, or the speed of light was faster, would allow structures to form and information to propagate more quickly, potentially explaining the rapid emergence of organized complexity we're observing. If gravity was stronger by even a small amount in those first billions of years, the whole timeline of structure formation could compress dramatically. What would normally take billions of years could happen in hundreds of millions. Others have proposed the primordial black hole hypothesis, the idea that some black holes formed not from stellar deaths but directly from the density fluctuations of the Big Bang itself. Born enormous, not grown enormous. Born with masses millions or billions of times that of the Sun, and born ready to act as seeds around which galaxies could rapidly organize. If this happened, and the conditions of the very early universe might have been right for it, it could explain much of what we're seeing. The massive black holes at the centers of early galaxies, the rapid galaxy growth that seems to have organized around them, the strange coevolution of galaxies and black holes that James Webb keeps uncovering. But direct evidence for primordial black holes remains elusive. The idea is compelling. The evidence is not yet conclusive. And then there are the theorists who have gone even further, who have suggested that the anomalies James Webb is uncovering might be consistent with the idea that our universe is a simulation, that its initial conditions were set by some external process, and that those initial conditions differ in subtle but profound ways from what we would expect if the universe arose naturally. That whoever or whatever set the starting parameters chose differently than physics alone would have demanded. This idea is not science in the traditional sense. It is not falsifiable in any straightforward way. Most physicists dismiss it, and they are probably right to do so, but it is worth noting that it is being discussed. That scientists who have spent their careers building and testing the standard model are now seriously considering ideas that would once have seemed like science fiction. Because that is how profound the challenge from James Webb's data actually is. Profound enough to push serious people to the edges of what they're willing to entertain. The scientific community is slowly, reluctantly, but unmistakably coming to terms with this. James Webb's findings are not measurement errors. They are not systematic biases in the data pipeline. They have survived every attempt to explain them away. They are a real feature of the early universe, confirmed by multiple instruments, multiple teams, across multiple regions of the sky. The data is real. The galaxies are real. The anomalies are real. And they demand an explanation that we do not yet have. Come back to this moment, to the quiet of this night, to the sky above you, and think about what we've covered. Out there, billions of light years away, there are galaxies with the wrong shape, galaxies with the wrong chemistry, galaxies with the wrong stellar populations, galaxies with black holes that grew too fast. And all of these wrongnesses are connected. All of them are pointing to the same gap in our understanding. A gap that James Webb is making impossible to ignore. A gap that grows wider with every new observation. A gap that might contain the outline of something new. Something we haven't yet thought of. Something we aren't yet equipped to imagine. The story is not over. In fact, we're just reaching the part where it gets truly strange. Because James Webb hasn't only found unusual galaxies in the early universe. It has found something that is not a galaxy at all. A structure whose very existence challenges not just our models of galaxy formation, but the most basic assumptions we make about the universe on the largest scales. A structure so large, so ordered, so geometrically precise that it violates a principle we have built the entire mathematical framework of cosmology upon. And this discovery has led some scientists to ask a question that would have been unthinkable just a few years ago. Did the Big Bang actually happen the way we think it did? Sleep now. Rest. Let the weight of what we've discussed settle. But carry that question with you into your dreams. Because in the next section, we're going to look at the deepest mystery James Webb has uncovered. A mystery that cuts to the very foundation of what we think the universe is. And it may be the most important question in all of modern science. Did the Big Bang actually happen? Let that question sit for a moment. Feel how strange it sounds, how almost offensive, how it seems to cross a line from serious science into something else, something more reckless. Something that belongs in a fringe magazine rather than an academic journal. Because the Big Bang is not just a theory. It is the foundation of modern cosmology. The backbone around which our entire understanding of the universe is built. The starting point from which every calculation, every model, every prediction flows. It is confirmed by so many independent lines of evidence that questioning it has always felt like questioning whether the Earth orbits the Sun. Something settled. Something beyond serious debate. And yet here we are. Because James Webb has found things that are causing some of the most careful, most rigorous cosmologists in the world to ask this question out loud. Not irresponsibly. Not sensationally. Not as an act of intellectual rebellion, but honestly, as scientists confronting data that pushes against the limits of their best theories. As people who have dedicated their lives to understanding the universe and who now find themselves face to face with something the universe is telling them they don't fully understand. In this section, I want to tell you about the strangest structure James Webb has found in the early universe. Not a galaxy. Not a black hole. Something that doesn't fit comfortably into any category in our standard model. A structure so large, so organized, so geometrically precise, that its very existence threatens one of the most fundamental assumptions we make about the universe at its largest scales. An assumption so basic that it is built into the very equations that describe the universe's expansion. An assumption that, if wrong, requires rewriting some of the most trusted mathematics in all of physics. But to understand why this structure is so troubling, we first need to understand what the Big Bang Theory actually rests on. What its foundations are. What pillars hold it up. Because the theory is stronger than most people realize. Far stronger. And you cannot appreciate how deeply James Webb's findings cut until you understand what they are cutting against. Until you understand what is actually at stake when the data doesn't fit. The Big Bang Theory stands on 3 pillars. The first pillar is the expansion of the universe. In 1929, Edwin Hubble made one of the most consequential observations in scientific history. Working at the Mount Wilson Observatory in California, using a 100-inch telescope that was the most powerful in the world at the time, he measured the distances and velocities of dozens of galaxies. And he found that distant galaxies are moving away from us. Not just a few of them, all of them, in every direction. And crucially, the further away a galaxy is, the faster it is moving away. There is a precise mathematical relationship between distance and recession speed, what we now call the Hubble law. This is not galaxies moving through space. This is space itself expanding, stretching, growing larger in every direction simultaneously, carrying galaxies along with it like raisins in a rising loaf of bread. And if space is expanding now, then if you run time backward, space was smaller in the past. Smaller and smaller as you go further back, denser and hotter, until you reach a moment, a singularity, where everything was compressed into an almost infinitely small, infinitely hot point. That moment is the Big Bang. The second pillar is the cosmic microwave background radiation. In 1965, radio astronomers Arno Penzias and Robert Wilson were using a large horn antenna in New Jersey to study radio signals from the Milky Way. They detected a faint signal coming uniformly from every direction in the sky. At first, they thought it was interference. They tried everything to eliminate it. They removed pigeons that had been nesting in the antenna. They cleaned out what they diplomatically described as white dielectric material from the horn. But the signal persisted, and when theorists examined it, they realized what it was. It was light, ancient, incredibly redshifted light from approximately 380,000 years after the Big Bang. The moment when the universe had cooled enough for electrons and protons to combine into neutral hydrogen. Before that moment, the universe was a hot, opaque plasma. Photons couldn't travel freely. They were constantly scattered, trapped in a fog of charged particles. But at that moment, the fog lifted, and the light that had been trapped in the plasma streamed out freely in all directions. That light has been traveling ever since, stretched by the expansion of the universe from visible wavelengths into microwaves. And it reaches us from every direction, remarkably uniform, with tiny fluctuations that encode the initial density variations from which all structure, all galaxies, all clusters, all the cosmic web eventually emerged. This cosmic microwave background radiation is not just evidence for the Big Bang. It is a detailed, high-resolution snapshot of the universe's initial conditions, a fossil of the universe's infancy, and it matches Big Bang Theory's predictions with extraordinary precision. This discovery earned Penzias and Wilson the Nobel Prize in Physics in 1978. The third pillar is the abundance of light elements. Big Bang nucleosynthesis, the production of hydrogen, helium, and lithium in the hot, dense early universe, is one of the most precise predictions in all of physics. We know the temperature, the density, the timescales. We know how nuclear reactions proceed in that extreme environment. We can calculate with high precision what fraction of the universe's matter should be in each element after the first few minutes. After the first 3 minutes of cosmic history, when the universe had cooled just enough for nuclear reactions to occur, but before it was too cool for them to continue. A narrow window, a brief period of cosmic nucleosynthesis. And when we observe the oldest, most pristine gas clouds in the universe, material that hasn't been contaminated by stellar processing, the abundances match the predictions almost exactly. The helium fraction, the deuterium abundance, the lithium content, all of it consistent with a universe that emerged from a hot, dense, rapidly expanding initial state, with a precision that rivals the best experiments in laboratory physics. These three pillars are not just consistent with the Big Bang, they essentially require it. There is no other coherent framework that explains all three simultaneously. No alternative model has ever been proposed that comes close to matching all three with the same precision. And this is why the Big Bang is not just accepted, it is considered one of the most firmly established theories in all of science. As solid as anything we know, until James Webb entered the conversation. Before describing what James Webb found, it's worth noting a paper published in 2023 by physicist Eric Lerner and collaborators. They analyzed James Webb data and made a controversial claim. The surface brightness of distant galaxies, the way their apparent brightness falls off with distance, matched a static, non-expanding universe model better than it matched the standard Big Bang expansion model. In other words, distant galaxies don't look quite the way they should if the universe is expanding as the Big Bang model predicts. The numbers, Lerner argued, fit better with a universe that isn't expanding at all. This claim is deeply contested. Most cosmologists reject Lerner's interpretation. They argue that his analysis doesn't properly account for evolution in galaxy properties over cosmic time. Galaxies don't stay the same as the universe ages, and not correcting for this would produce exactly the kind of apparent discrepancy Lerner reports. The mainstream response was clear and largely dismissive. But the very fact that this argument is being had, that a paper questioning the expansion of the universe is being taken seriously enough to be published, cited, and debated is significant. Not because Lerner is right, perhaps he isn't, but because the climate of certainty that used to surround Big Bang cosmology has cracked. James Webb has opened questions that were previously considered closed, and that opening, regardless of how it is eventually resolved, changes the nature of the scientific conversation. The door is open in a way it wasn't before, but the far more serious challenge came from something else entirely. Something James Webb detected in the late months of 2023 that stopped many cosmologists in their tracks. Something that didn't require any disputed statistical analysis. Something that was simply there in the images and the data demanding to be explained. A structure, a vast, organized, almost geometrically precise structure in the early universe, extending across many millions, perhaps hundreds of millions of light years. An alignment of galaxies so ordered, so regular, so far beyond anything that gravitational physics should be able to produce in the time available, that it violates one of the most fundamental assumptions of the standard model. Not a minor violation, not a small tension, a direct confrontation with a principle that the entire mathematical framework of cosmology depends upon. That assumption is called the cosmological principle, and it states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous meaning matter is distributed roughly uniformly. No special locations. No dramatic differences between one region and another when you zoom out far enough. Isotropic meaning the universe looks the same in all directions. No preferred axis. No special direction. Just a smooth, even distribution of matter and energy when you look at scales large enough to average out local variations. This principle is not just a philosophical preference. It is not merely an assumption of convenience. It is a mathematical requirement for the standard model to work. The equations that describe the expansion of the universe, the Friedmann equations derived from Einstein's general relativity, assume homogeneity and isotropy. They were derived under that assumption. They only describe the universe correctly if that assumption holds. If the universe is not homogeneous and isotropic on large scales, those equations don't apply in the way we've been using them, and everything built on top of them has to be reconsidered. The cosmological principle is well supported by observations of the modern universe. On scales larger than a few hundred million light-years, matter distribution is indeed fairly smooth. The cosmic microwave background is uniform to 1 part in 100,000. The large-scale structure surveys show that while there are filaments and voids and clusters, the overall distribution averages out to something close to homogeneous. The principle holds, or it appeared to hold, but there are cracks. Even before James Webb, there were structures that pushed against the cosmological principle. The Hercules-Corona Borealis Great Wall, a structure of galaxies roughly 10 billion light-years long, was described in a 2014 paper as potentially too large to be consistent with the cosmological principle. 10 billion light-years, a structure larger than most of the observable universe's diameter. The giant arc, a 3.3 billion light-year-long curved structure of galaxies described in 2021, raised similar concerns. Structures of this size should not exist if matter is truly distributed uniformly on large scales. And now James Webb is finding organized structures in the early universe. In a period when the universe was so young that structures this organized should be even more impossible than they are today, because there was even less time, even less opportunity for anything this orderly to have assembled. Gravity is slow. It builds structure from the bottom up. Small overdensities attract slightly more matter. Slightly larger overdensities attract more still. Over hundreds of millions of years, filaments and walls and clusters emerge. But this process has a speed limit. The largest structures gravity can build in a given time are bounded by how far gravitational influence can propagate in that time. Bounded by the distance light can travel. Bounded by the age of the universe. On scales beyond a certain size, there simply hasn't been enough time for gravity to organize matter into coherent structures. The physics enforces a maximum size on any organized structure at any given epoch of cosmic history. The structures James Webb is finding violate this limit. They are more organized, more aligned, more geometrically coherent than gravity should have been able to produce in the time available. Which means either gravity in the early universe worked differently than it does today, or these structures formed through a mechanism other than the gradual gravitational assembly we've been assuming, or the universe is older than we think, or the Big Bang produced initial conditions very different from what we've modeled, or something else entirely, something we haven't yet imagined, was at work. Each of these possibilities is profound. Each one requires revising something we thought we understood, something we've been assuming without question. Each one opens a door onto territory that cosmology has barely begun to explore. The cyclic cosmology models, proposed independently by theorists like Roger Penrose, Paul Steinhardt, and Neil Turok, offer one possible framework. In these models, the Big Bang was not the absolute beginning of everything. It was a transition, a bounce, a moment when a previous cosmic cycle ended and a new one began. In Penrose's conformal cyclic cosmology, the distant future of one universe, after all black holes have evaporated and the universe has stretched to near-perfect uniformity, becomes, through a mathematical transformation, the initial conditions for the next universe. A death that is also a birth, an ending that contains a beginning. In Steinhardt and Turok's ekpyrotic model, two higher-dimensional brains, membranes in a higher-dimensional space, collide periodically, and each collision generates a new Big Bang, a cosmic cycle playing out on scales and in dimensions that we cannot directly perceive. In both frameworks, the Big Bang carries forward information from what came before. Patterns, structures, correlations that were imprinted in the previous cosmic cycle show up as organized features in the new one, like a memory encoded in the initial conditions, a kind of cosmic inheritance. And these inherited features could, in principle, explain why the early universe appears more organized than standard Big Bang theory predicts. The organization was not built from scratch. It was carried forward from something that existed before. None of this is confirmed. None of this is even close to being testable with current technology. These ideas live at the frontier of theoretical physics, where the mathematics is rich but the observational handles are thin. But the fact that these ideas are being taken seriously, that they are being discussed as potentially relevant to what James Webb is finding reflects just how deep the current cosmological crisis goes, how genuinely unsettled the foundations are becoming. Another avenue of investigation involves the details of cosmic inflation. The standard inflationary model, the idea that the universe underwent an extraordinary period of exponential expansion in the first tiny fraction of a second, was developed in the 1980s to solve several problems with the original Big Bang model. It explains why the cosmic microwave background is so uniform. It explains why the universe's spatial geometry is so flat. And it predicts the spectrum of initial density fluctuations from which all structure emerged. The seeds of galaxies, the seeds of clusters, the seeds of the cosmic web, all of it encoded in the quantum fluctuations of that brief inflationary period. But inflation is not a single model. It is a class of models, a framework, not a unique theory. And different inflationary scenarios predict different details of those initial fluctuations. Some inflationary scenarios can produce significantly larger and more organized initial structures than the standard model predicts. Structures that are more coherent, more correlated, more geometrically ordered than the most common versions of inflation would generate. And if one of these alternative inflationary scenarios turns out to be correct, it could explain much of what James Webb is seeing: the large-scale structures, the rapid galaxy formation, perhaps even some of the chemical anomalies. The solution might be hiding in the details of the universe's first trillionth of a trillionth of a trillionth of a second. A moment so brief and so extreme that it lies far beyond any direct observation, but whose consequences, if we read them correctly, might be written in the structures James Webb is finding. The CMB-S4 experiment, a planned next-generation cosmic microwave background telescope, will measure the polarization of the cosmic microwave background with unprecedented precision. Different inflationary models leave different imprints in this polarization pattern. Subtle differences in the way the radiation is polarized across the sky. Differences that carry information about what happened in that first extraordinary moment. And by mapping it in sufficient detail, scientists hope to be able to distinguish between competing inflation models, to determine which version of inflation, if any, correctly describes the universe's birth. This is potentially how we answer the question of which early universe scenario is actually correct. This is the next great test. But that experiment hasn't happened yet. The data isn't in yet. And in the meantime, James Webb keeps looking, and keeps finding things that challenge our assumptions, keeps accumulating evidence that something about our picture of the early universe is incomplete, keeps reminding us that the ocean of truth is larger than we thought. What does all of this mean? What is the takeaway from an ever-growing list of anomalies that our best models cannot explain? It means the standard cosmological model, as successful as it has been, is incomplete, perhaps significantly incomplete, in ways that will require not just adjustment but genuine new physics, new ideas, new frameworks, new ways of thinking about the beginning and structure of the universe, ways of thinking that don't yet exist, that need to be invented, that will be invented by someone someday because the data demands it. The history of science tells us that this is how progress happens. Every great theoretical revolution was preceded by anomalies, data points that didn't fit the prevailing framework, tensions that grew until they could no longer be ignored, observations that quietly, patiently insisted that the old picture was incomplete. The anomaly of Mercury's orbit foreshadowed general relativity. The ultraviolet catastrophe foreshadowed quantum mechanics. The anomalous expansion of the universe foreshadowed dark energy. James Webb's impossible galaxies may be foreshadowing something equally profound, something we cannot yet fully imagine, something that will, in retrospect, seem inevitable, as all great discoveries seem inevitable in retrospect. being alive at this moment in science is a remarkable privilege. We may be the generation that witnesses the next great paradigm shift in cosmology, the next revolution in our understanding of where we came from. And James Webb is the instrument making that moment possible, the chisel cutting into the stone, the lens through which the universe is beginning to reveal what it has been hiding. The analysis will continue for years. Some anomalies will be resolved. Others will deepen. New theories will emerge. Old certainties will be questioned. And eventually, perhaps 10 years from now, perhaps 50, the outline of a new understanding will begin to take shape. A new picture of the early universe, more complex than the old one, more surprising, and ultimately more true. But tonight, when you look up at the sky, hold this thought. Out there, billions of light years away, there are structures that should not exist under the laws of physics as we understand them. There are galaxies that defy our models of formation. There are chemical abundances that exceed what the timeline allows. There are organized patterns on scales that gravity couldn't have produced in the time available. All of these are messages. All of these are the universe speaking to us. In light, in chemistry, in geometry, and James Webb is learning, slowly and painstakingly, to translate what it's saying. But the translation is not finished. And the most unsettling part of the message is still coming. Because beyond the galaxies, beyond the large-scale structures, James Webb has uncovered evidence that challenges something even more fundamental. The nature of the invisible substance that we believe holds the universe together. Dark matter, the subject of the next section. And if what James Webb is suggesting about dark matter is true, it means we are wrong about 27% of everything. 27% of all the mass in the universe. The backbone of cosmic structure. The scaffold on which all galaxies are built. If we have misunderstood that, we have misunderstood far more than we realized. Close your eyes, rest, and sit with this question. Did the universe begin the way we think it did? Or is there something written in the earliest light, something James Webb is only now beginning to read, that tells a different story entirely? Dark matter. Two words that represent one of the most profound mysteries in all of modern physics. We cannot see it. We cannot touch it. We cannot detect it directly with any instrument we've ever built. We have never held a dark matter particle in our hands. Never watched one decay. Never created one in a laboratory. And yet we believe it makes up roughly 27% of the total mass energy content of the universe. More than 5 times the mass of everything visible. Every star, every planet, every nebula, every galaxy we've ever observed. All of that visible matter. All of it. Every photon of light, every atom of hydrogen, every supernova remnant, every quasar blazing at the edge of the observable universe. All of it is only a small fraction of what's actually out there. The rest, the majority, is dark, silent, invisible, and currently beyond our ability to directly detect. We know dark matter exists, or at least we believe very strongly that it does, because of the gravitational effects it produces. Without it, the math of the universe simply doesn't work. Galaxies spin too fast. Their outer stars rotate at speeds that should tear them apart if only visible matter is holding them together. Galaxy clusters hold together when they shouldn't. The hot gas binding them in place would disperse in a fraction of the cluster's age if there weren't far more mass than the visible matter can account for. The large-scale structure of the cosmic web could never have assembled in the way we observe it. The filaments and walls and voids would not have the sizes and distributions we measure. Dark matter provides the gravitational backbone around which everything else organizes. The skeleton of the universe, invisible but essential, the silent majority upon which all visible structure depends. Or so we believed, Because James Webb has now produced findings that put even this cornerstone of our cosmological model into question. Findings about dark matter's distribution in early galaxies, about its total abundance, about its possible behavior, and one extraordinary, unexpected, still unresolved observation that has some scientists daring to wonder if we have finally, for the first time, glimpsed dark matter directly. Not inferring its presence, not deducing it from the motion of stars, but actually detecting it through its own radiation. To understand why these findings are so unsettling, we need to go back to the beginning of the dark matter story, back to where the trail begins, back to the first person who looked at the data and said, "Something is missing." The first hint that something was missing came in the 1930s. Fritz Zwicky was studying the Coma cluster, a large collection of hundreds of galaxies in the constellation Coma Berenices. He measured how fast the individual galaxies within the cluster were moving, and he noticed something strange, something that should not have been possible. They were moving far too fast. If the only gravity holding the cluster together was the gravity of the visible stars and gas, those galaxies should be flying apart. The velocities were far too high to be bound by visible mass alone. The cluster should have dispersed long ago. Something else had to be providing the gravitational glue. Something invisible, something massive, something present throughout the cluster, holding it together against the centrifugal tendency of its rapidly moving members. Zwicky called it Dunkel Materie dark matter, but he was decades ahead of his time. The idea wasn't taken seriously. It was considered too speculative, too radical, too much a departure from established physics. And so it waited. It took Vera Rubin working in the 1970s to bring dark matter into the mainstream. Rubin measured the rotation curves of spiral galaxies, the relationship between how fast stars are orbiting and how far they are from the galactic center. According to Newtonian mechanics, stars far from the center should orbit more slowly, just as the outer planets of our solar system orbit more slowly than the inner ones. The force of gravity falls off with distance. The further out you go, the slower the orbit. This is one of the most basic and well-tested predictions of gravitational physics. But Rubin found something completely different. The outer stars of galaxies were orbiting just as fast as, or sometimes even faster than, the inner ones. The rotation curves were flat when they should have been falling. Dramatically, unmistakably flat. As if there was mass distributed throughout the entire galaxy, including far out in the halo, maintaining the gravitational pull even at large distances. The only explanation was that there was far more mass in these galaxies than the visible stars and gas could account for. Mass distributed in a large halo extending well beyond the visible disk of the galaxy. Invisible mass, dark matter. This finding was confirmed and reconfirmed across hundreds of galaxies by different researchers using different techniques over the following decades. Gravitational lensing, the bending of light around massive objects, revealed the same invisible halos, the same excess mass, the same presence of something unseen but gravitationally real. The dynamics of galaxy clusters confirmed the same missing mass. The cosmic microwave background's precise fluctuation pattern required dark matter to be present in the early universe, seeding the gravitational wells into which ordinary matter later fell. Dark matter became a cornerstone of cosmology, not as speculation, not as a placeholder, as a well-supported, multiply-confirmed pillar of our understanding of the universe. But here is what we still don't know: what dark matter actually is, what particles it consists of, how it was produced in the early universe, why it doesn't interact with light, whether it interacts with itself in any way beyond gravity. Decades of searches in underground laboratories shielded from cosmic rays, at particle accelerators like the Large Hadron Collider, using space-based gamma-ray detectors, have found nothing. No dark matter particle. No direct detection signal. No smoking gun. Just the ongoing, unresolved mystery of what this dominant component of the universe actually consists of. The identity of the thing we are most certain exists but cannot identify. And now James Webb is adding a new layer to that mystery. A layer that is deeply troubling. Not because it suggests dark matter doesn't exist, but because it suggests that the dark matter we know exists is not behaving the way our models say it should. When James Webb observed early galaxies, the distribution of dark matter within them, inferred indirectly from the motions of stars and gas, was not what the Standard Model predicts. According to the Standard Model's best simulations, dark matter should be densely concentrated at the centers of galaxies, forming a cuspy, peaked density profile that rises steeply toward the galactic core. The inner regions of galaxies should be dominated by dense dark matter, a gravitational spike at the center. This prediction, known as the NFW profile after the researchers Navarro, Frank, and White who derived it, is one of the most robust predictions of standard cold dark matter cosmology. It has been confirmed in many observations of galaxies in the modern universe. It has been reproduced in countless high-resolution simulations. It is considered one of the bedrock predictions of the dark matter model. But in some of James Webb's early galaxies, the profile is wrong. The central density peak isn't there. Instead of a steep central cusp, there's a flat core, a roughly uniform distribution of dark matter rather than a sharp concentration. The center looks more like a plateau than a peak. This is called a core halo profile, and it is very difficult to explain with standard dark matter physics. Physicists have known about this discrepancy, sometimes called the core cusp problem, for years in nearby galaxies. But James Webb is now finding it in early galaxies too, at cosmic distances, in a period when the universe was young, suggesting the problem is not just local, not just recent, but fundamental and ancient. One potential explanation is a modification of dark matter's fundamental properties. In the Standard Model, dark matter is assumed to be cold and collisionless. Cold meaning it moves slowly compared to the speed of light. Collisionless meaning dark matter particles don't interact with each other. They pass through each other like ghosts. No collisions, no scattering, no forces between dark matter particles beyond gravity. But what if dark matter particles do interact with each other? What if there are forces, undiscovered exotic forces, that act between dark matter particles in the same way that electromagnetic forces act between ordinary matter particles? This is called self-interacting dark matter. It is a model that has been seriously studied for decades, and it naturally produces flatter central density profiles. When dark matter particles scatter off each other, heat is transferred from the denser central regions outward, smoothing out the central cusp and creating a flat core. Exactly what James Webb is observing in some early galaxies. Self-interacting dark matter is not a new idea. It was proposed to resolve discrepancies between simulations and observations at small scales, but it has never been confirmed. And James Webb's findings are now adding to the weight of evidence that something unusual may be going on with dark matter's behavior. If dark matter is self-interacting, it changes how we understand virtually every dark matter prediction. Every simulation would need to be revised, every prediction recalibrated. It would be a significant step forward in understanding the universe's most mysterious component. The second and more radical possibility is one that dark matter researchers have always resisted. Maybe dark matter doesn't exist. Maybe the gravitational anomalies we attribute to it are not due to invisible matter at all, but to a modification of how gravity behaves at very low accelerations. A different physics, not a different substance. This is the core claim of modified Newtonian dynamics (MOND), proposed by Israeli physicist Mordechai Milgram in the 1980s. MOND says that below a certain critical acceleration, about 1/10 of a billionth of a meter per second squared. Gravity doesn't follow the standard inverse square law. It falls off more slowly. And this deviation from standard gravity, rather than the presence of extra invisible matter, is what produces flat galaxy rotation curves. Not dark matter, just gravity working differently than Newton described at very low accelerations. MOND has a remarkable track record at galaxy scales. The precision with which it predicts galaxy rotation curves from visible matter alone is genuinely impressive. It is not just a qualitative fit, it is quantitative, tight. With a single free parameter, that critical acceleration, it successfully predicts the dynamics of a wide variety of galaxies, including dwarf galaxies where dark matter models often struggle. A level of precision that is genuinely surprising. But MOND fails at larger scales. Cannot explain galaxy cluster dynamics without adding additional mass anyway. It cannot reproduce the pattern of baryon acoustic oscillations in the cosmic microwave background. It cannot explain the large-scale structure of the cosmic web. And in all these failures, the dark matter model succeeds. So the consensus has long been that MOND is an interesting curiosity that captures something real at galaxy scales, but cannot be the fundamental theory. Partial truth, not a complete one. James Webb's findings are reigniting this debate, because the dark matter distribution anomalies in early galaxies, those flat central cores where there should be steep cusps, are more consistent with MOND's predictions than with standard cold dark matter. And the apparent deficit of dark matter in some early galaxies makes the situation even more interesting, not proving MOND right, but making the dismissal of its insights harder to sustain. A 2023 study added another dimension to this picture. Researchers used James Webb data to attempt to measure the dark matter content of some early galaxies directly. And in some cases, they found that the observed dynamics of these galaxies could be reproduced with far less dark matter than standard models require. In the most extreme cases, some galaxies appeared to function normally even with very little dark matter at all. Their stellar dynamics consistent with a scenario where dark matter's role was far more limited than we assumed. This is explosive if confirmed, because dark matter is not just a detail of galaxy formation. It is the backbone of everything. The cosmic web cannot assemble without it. The initial density fluctuations that seeded all structure cannot grow into the observed large-scale structure without it. The Big Bang nucleosynthesis predictions don't match observations without it. If dark matter is substantially less abundant than we think, or if it behaves in fundamentally different ways, then the entire cosmological model needs to be rethought from the foundation. Not adjusted, rethought. But, and this is important, we need to be careful about overinterpreting these early results. Measuring dark matter content in early galaxies is technically extremely difficult. The uncertainties are large. The methods are indirect. Alternative explanations for the observed dynamics exist. And extraordinary claims require extraordinary evidence. Science has been burned before by preliminary results that didn't survive scrutiny. The findings are interesting and suggestive, but they are not yet conclusive. The debate is genuine, and it will continue. What is conclusive, however, is that James Webb is generating results about dark matter's behavior in the early universe that our best models did not predict and currently cannot fully explain. And that alone is significant. That alone demands attention. That alone justifies a genuine reopening of questions we thought were settled. Now let's turn to perhaps the most extraordinary of James Webb's dark matter-related discoveries. Something that was found almost by accident. Something that no one was specifically looking for. Something that emerged from the data unexpectedly and has not yet been fully explained. While studying the environments around some early galaxies, James Webb detected a faint, diffuse radiation that cannot be attributed to any known astrophysical source. Not stars, not gas emission lines, Not AGN activity, not dust scattering, something else. Something whose spectral signature doesn't match anything in our catalogs of known objects and processes. A signal from somewhere we didn't expect. A light from a source we cannot identify. One hypothesis, speculative but scientifically serious, is that this unidentified radiation is the signature of dark matter annihilation or decay. If dark matter consists of particles with finite lifetimes, those particles would occasionally decay, releasing energy as photons. A slow, steady glow from the dark matter halos surrounding galaxies. Very faint, very diffuse, but potentially detectable with an instrument as sensitive as James Webb. Or if dark matter particles and antiparticles occasionally meet and annihilate each other, that annihilation would produce a characteristic radiation signature, a spectral fingerprint that should be specific to the mass and properties of the dark matter particle. Either process would produce a very faint, diffuse glow whose spectral properties would be determined by the fundamental nature of dark matter itself. The search for this signal has been ongoing for decades. Underground detectors listening for dark matter particles striking atomic nuclei, listening in the deepest mines on Earth, shielded from cosmic rays, waiting in the dark for a signal that has never come. Space telescopes looking for gamma rays from dark matter annihilation in the cores of galaxies, scanning the sky for an excess of energetic photons that could only come from dark matter. Particle accelerators trying to create dark matter particles in high-energy collisions, hoping to produce in a laboratory what the Big Bang produced in the first moments of the universe. None of these searches has found a definitive signal. Not one. In decades of searching, until possibly James Webb detected something anomalous that might be what we've been looking for. It is too early to be certain. The signal could have other explanations. More data and more analysis are needed. Independent confirmation from other instruments would be required. Before any claim of dark matter detection can be made, the bar of evidence must be extraordinarily high. But the possibility is real enough that it is being taken seriously. Because if this is a dark matter signal, then James Webb has achieved, accidentally, what decades of dedicated experiments could not. The first direct glimpse of the substance that makes up more than a quarter of the universe. The first time humanity has ever actually detected dark matter, rather than inferring its presence. A discovery that would rank among the greatest in the history of science. Step back and take in the full picture of everything this section has covered. Dark matter profiles in early galaxies that don't match our predictions. Galaxies in the early universe that appear to contain less dark matter than they should. An unidentified radiation signal that just might, be the long-sought signature of dark matter annihilation or decay. None of these alone is definitive. None of them alone is enough to overturn the dark matter model. But together, they paint a picture of a substance whose true nature is significantly different from what we've assumed. More complex, more surprising, less completely understood than we were comfortable admitting. We are certain that something produces the gravitational effects we attribute to dark matter. We are certain that whatever it is the dominant form of mass in the universe. We are certain that it played a crucial role in the formation of all cosmic structure. It is real. Its effects are real. Its presence is written into the structure of everything we observe. What we are not certain of, what James Webb is now calling into serious question, is our model of what it is, how it behaves, and how it was distributed in the early universe. This matters, not just as an abstract scientific puzzle, not just as an academic exercise in cosmological theory, but because dark matter is part of the answer to the question of why we exist. Without dark matter, the universe's structure would be radically different. The cosmic web would not form the way it does. The right kinds of galaxies in the right kinds of environments would not emerge. The conditions that allow stars like our Sun, and planets like our Earth, and life like ours to exist might never arise. Dark matter is woven into the story of our own existence, into the chain of events that led from the Big Bang to you. And if we have misunderstood it, we have misunderstood part of the story of where we came from. The anomalies are real, the questions are genuine, and the answers, when they come, will almost certainly require new physics, new ideas, new ways of thinking about the fundamental constituents of